Our next oral presentation is from Ehsan Saberian from Netflix, and he will discuss a kind of an interesting fusion between gradient boosted decision trees and neural networks.
Yeah. All right. My name is Ehsan, and this is a joint work with my colleagues Pablo and Eve. And I'm going to show you that we can represent a collection of decision trees in a single neural network. Now, if you have been in industry for a couple of years, you know that unlike academia, GBDTs are still very popular here. And they are fast, they are accurate, they have low memory footprint, we can deploy them easily to production. But training has always been challenging because tree training is based on a node splitting that's greedy. And if you train GBDT, it's sequential. You have to train one after each other. And it's also not incremental or end-to-end. What it means is that if you get new data points, you have to retrain from scratch. On the other hand, neural networks have been very popular recently. There have been a lot of innovations. They're compatible with incremental training, end-to-end training, and transfer learning. And the question is, can we bring GBDT to the neural network land and take advantage of these benefits? And to answer that, where is it? Okay. And to answer this, we need to go back to the basic and ask, what's a decision tree? And here is an example. And you can see that a decision tree is a collection of leaf nodes that are gated by some AND condition. So if I want to describe this leaf node, it's basically saying if F1 is less than T1 and F2 is less than T2, then we output 1.3. So for every leaf node, I can represent it as an if statement. And we can do this for the rest of the leaf nodes. And we can flatten our tree in a bunch of these if statements. And the good thing about these if statements is that we can simply implement them in a neural network. There could be many implementations. This is one example of it. Assume that I have a feature vector F1 and F2. I will do a transformation and transform this two-dimensional vector to a four-dimensional one, which is a binary transformation, into F1 less than T1, F1 greater than T1, F2 less than T2, and F2 greater than T2. Now I can simulate that AND condition by putting a neuron over there that is connected to F1 less than T1 and F2 less than T2. And if you set the right weights and right bias and use a step function as activation function, this neuron can simulate the AND logic for you. And then we have an outer node that's going to accumulate 1.3 if this neuron is active. So I can translate that if statement into a neuron, and I can do it for all the other if statements or all the other leaf nodes. In fact, if you have a GBDT, which is a collection of 100 trees, you can get all the leaf nodes from all of those trees and put them in this middle layer. And that's how we convert this whole GBDT into a single network, which is by itself interesting. You can convert your trained GBDT into a neural network and have some fun with it. But really, we don't want to train GBDTs. And the question is, can we learn this network directly? And the answer is kind of obvious. Why not? We have trained everything. So if you look at this network, the top part is a simple regular neural network. And we can train it with all the regular tricks that we do. We approximate the step function with the ReLU. We remove all the constraint on binary and stuff like that. So that's easy. The tricky part is this bottom part, which we do like feature thresholding. And the main question really is, how do we come up with these thresholds? And the strategy that we propose is basically we provide all the possible thresholds to the network, and we let the network choose what threshold it needs. But the problem is that providing all possible thresholds is not practical. But the key point is that we only need to provide the relevant threshold. Let me give you an example. Let's say you have a training data, and in your training data you have a feature, and in this feature there is no value between 2 and 3. So any threshold, let's say 2.1 or 2.2 or 2.5, they all look the same when you want to split this data. So you actually don't need 2.1, 2.2, or 2.5. You really just need the feature values that you see in your training data. And that by itself is a huge reduction. You go from the space of all real value to some discrete values that you're going to observe in your training data. But still, if you have a continuous value or continuous variable, you will end up with a lot of values in your training data, and it's going to be inefficient. Luckily, we can use quantization. And quantization has been around for many years and has been used in a lot of these fast decision tree learning algorithms like XGBoost and others. And they have been shown that if you quantize your data into 50 or 100 bins, you don't lose much in accuracy. And if we do this trick, we will end up with 100 to 50 thresholds per feature. That's pretty much manageable. And we can go and train our network. But before going there, we can do one more simplification. So if you remember, in a decision tree, we have two nodes. It's the less than the threshold route and a greater than the threshold route. And that's how we encoded our transformation. We have less than T1 and greater than T1. Instead of this binary translation, we can have another translation that basically says F1 less than T1, F1 between T1 and T2, and so on and so forth. These two representations are going to give you the same amount of information, but the second one is much more compact. And the other interesting part is that the second one is actually a quantization mechanism. You just do quantization and then do one hot binary encoding, and you're done. And that's what we call Hammock, which is a simple neural network with one layer, which is a hidden layer, and a simple transformation, which is basically quantization and one-hot encoding. And the reason that we call it Hammock is because Hammock is a combination of trees and net, and it's going to provide you with more joyful and relaxing experience. This simple neural network has a couple of interesting properties. First of all, the decision function is very similar to decision tree, so it has all the nice interpretability properties that we need. And then there are all these tips and tricks that we do in decision tree boosting, like we do leaf pruning. If you add regularization on the top layer over there, you have leaf pruning. We do feature sampling, or we do sampling. And if you do dropout on the first layer, you have your equivalent of feature sampling or like sampling. The other interesting part is that if you look at the final predictor of this model, it's pretty simple. You have quantization and then two matrix multiplication, which, by the way, the first matrix multiplication is a sparse. Now, if you don't want to deploy TensorFlow in your production path or in your critical path, you can implement this thing in 20 lines of your favorite languages. In terms of performance-wise, we compared it with XGBoost, logistic regression, simple one-layer neural network, and tested it on 6 UCI data sets that were small and one internal Netflix data set that was big. And it was interesting that this simple neural network was able to give competitive result to XGBoost, which was like 100 decision trees of depth 5. And in terms of implementation, if you want to give it a try, it's super simple. If you are already in the TensorFlow environment, it's been already provided by TensorFlow. It's called bucketized feature column, which basically you provide a bunch of thresholds, and it will do the quantization for the feature for you. Then you can wrap it inside an indicator column, and you're done. If you're not in the TensorFlow environment, we're going to open source our implementation very soon. But really, the implementation is just a wrapper around the TensorFlow and bucketized feature column. We actually had to wrap it so that you don't see how simple it is. But we will announce it pretty soon. So in summary, all right, yeah. In summary, we introduced Hammock, which is a one-layer neural network with some input quantization. And this can bring GBDTs into the neural network land, and it will open up a lot of opportunities for incremental training, end-to-end training. And we can do a lot of new innovations and bring them inside the neural GBDT land, like adding more layers. We can replace the indicator or one-hot encoding with embeddings. We can do batch normalization. We can do network compression if it becomes too hard. So there are a lot of potentials, and we're very excited about it. And that's it. Thank you.
Hi, thanks for the talk. In the beginning, you mentioned that one of the disadvantages of the trees is that when you get new data, you have to retrain, and it seems like you're kind of bypassing that with the quantization. But if new data comes in that would make you change your quantization scheme, do you have to start the whole process from the beginning, or is there some way to sidestep that?
Typically, the feature distribution don't change that much, and we have, like at least in industry, we don't let the model to go stale more than a week or so. So
Okay. Yeah,
we will do it again anyways.
Okay.
I have a two-part question. First, you said the hidden layer which you form is compares one feature at a time, but feature dimension can be very long. And how long is your hidden layer then? Will it be very big hidden layer? How would you handle that?
So like in the experiment, I was trying with like 1,000 hidden nodes and like 10,000 hidden nodes. It's just the matter of like how big your GPU is and how much it can handle. Overall, the network is super simple. It's just 2 matrix multiplication.
And the second part, it's the gradient boosting is kind of an assemble learning. You have multiple trees. So where's the assemble part goes on then?
Can you say again?
Gradient boosting is more of an assemble learning, right? And where the assemble part goes on then, like?
Oh, okay. So they took my slide, but I had a slide about that.
Okay.
So if you look at the way that we constructed this hammock, let's say you have this middle layer, and you can assume that every 5 hidden node is associated with 1 tree. Okay. So you can put up some complex scheme that says, okay, I'm going to freeze the weights of the first 5, or wait, I'm going to freeze the rest of weights of everything else except this first 5, and then learn this one, and then freeze the other one, and then sequentially you can train every 5 nodes, assuming that you're training a new tree that way. But really, it's going to give you all of the troubles that we have so far, which was we don't like sequential training. So why not just let it go and then add a lot of regularization and dropout to bring more generalization?
Thank you.
Thank you. That's all the time we had. So let's thank Ehsan again for an excellent talk. Thank you.